Ever feel like technical interviews are designed to trip you up?
Oh, definitely. Sometimes it feels that way.
You're not alone. Today, we're diving deep into the kind of questions that often surface in these, well, high-stakes conversations. The ones that really test your understanding beyond just, syntax.
Exactly. It's less about just knowing the answer, more about how you get there, your thought process.
Right. So our mission today is to unpack some examples of these, let's call them tough technical interview questions. We want to give some insights into how to approach them, hopefully turn those stumbling blocks into, well, aha moments.
And the examples we're using, they're drawn from real interview experiences, right? So quite practical.
Yes, exactly. Real world stuff. It's interesting, like you said, how these questions act as a proxy for evaluating how you tackle actual engineering challenges.
Yeah, it's not usually about just reciting API details. It's about showing that structured thinking.
Okay, let's get right into it then. What often comes up first? Practical coding tasks.
The hands-on stuff.
So imagine you're in an interview and they ask, given a list of objects, say employees with salaries, how would you filter this list based on a specific condition? Like, find all employees with a salary greater than $40,000 using modern Java features, like streams. How do you tackle that?
Well, the most straightforward way using streams would be to use the filter operation.
Okay.
You'd take your list, convert it to a stream, employees.stream. Then inside the filter, you'd put a lambda expression, something like employee-employee.getSalary 40,000.
Lambda check.
Exactly. And that gives you a new stream with just those employees. Then you'd probably collect it back into a list.
Got it. Simple enough for a starting point. Now, what if they build on that? Like, how would you extend that filtering task to include a range, say salary greater than $40,000 and less than $50,000. Can you do that by combining separate conditions, maybe predicates?
Yeah, that's a good follow-up. And this is where using predicate objects really shines.
Okay, predicate.
So instead of putting all the logic right into the filter lambda, you can define separate predicate objects, like predicate employee is salary above 40K equals EEE.getSalary 40,000.
Yeah.
And another one, predicate employee is salary below 50K equals EEE.getSalary 50,000. Then in your filter, you combine them using .and. So filter a salary above 40K and a salary below 50K.
Chaining them together.
Exactly. And the real benefit here, which interviewers often look for, is the organization and reusability. Imagine those salary thresholds. Maybe they come from UI filters or different config values.
Right, not hard-coded.
Yeah. Keeping them as separate predicates makes the code much cleaner, much easier to manage and test.
That reusability point is key, isn't it? Thinking beyond just this specific problem, the source material we're looking at also hammers this home. Pay attention to follow-up questions.
Yeah.
Ones that add complexity or ask you to refactor.
Precisely. They want to see how you adapt, how flexible your thinking is. It's not just about the first answer.
Yeah.
And never hesitate to ask for clarification if a question seems a bit vague or ambiguous.
Oh, absolutely. Better to ask than guess wrong.
For sure. It shows you're careful, you want to solve the right problem. It's way better than just jumping in based on an assumption.
Okay, let's move on then. Another big area. Fundamental Java knowledge and keeping up with, well, new stuff.
Poor concepts, yeah.
So an interviewer might ask, apart from streams, what other important Java features have you used? What are some good examples there?
Well, two big ones usually come to mind for Java 8 onwards. First, the datetime API. Local date time.
Oh yeah, much better than the old date and calendar.
Way better. Less error prone, more intuitive. So that's a great one to mention. Second, default and static methods in interfaces. Also from Java 8.
Right, changing how interfaces work.
Exactly. Default methods let interfaces evolve without breaking everything that implements them. And static methods are useful for utility functions related to the interface. It was a pretty big shift.
Definitely key enhancements. And sticking with that theme, a very likely question now is, are you familiar with features in recent Java versions like Java 17 or Java 21? Can you describe some? What jumps out?
Okay, so Java 17, sealed classes are pretty interesting.
Sealed classes, right. Control over inheritance.
Yeah, you explicitly say which classes can extend or implement your class or interface. Gives you more control over your type hierarchy, can make code safer, more predictable.
Yeah.
Also in 17, you had enhancements to switch expressions, making them, well, more powerful and less verbose. And the Jakarta EE integration was significant for enterprise folks.
And Java 21.
The big one in 21 is virtual threads. Project Loom finally landing.
Ah, lightweight concurrency.
Exactly. They're managed by the JVM, not directly tied one-to-one with OS threads. It makes writing highly concurrent applications, especially IO-bound ones like microservices, much, much easier and more efficient. Huge potential performance gains without complex async code.
It really shows you need to keep learning. The language doesn't stand still.
Absolutely.
Now, let's get into core design principles. A classic. Can you describe the solid principles? Why are these still so important?
Oh, solid. Yeah, fundamental stuff for object-oriented design. They aim to make software easier to understand, more flexible, maintainable, all the good things.
So let's break them down. First, S.
Single responsibility principle. Basically, a class should have only one reason to change, one main job.
Like, don't mix database logic and configuration reading in the same class.
Exactly that. Keep concerns separate. Improves testing too, right?
Yeah.
You can test each part in isolation.
Makes sense. Okay, your way.
Open-closed principle. Software entities, classes, modules, whatever, should be open for extension, but closed for modification.
Extend, don't modify.
Right. You should be able to add new features without changing the existing working code. Think inheritance, composition, strategies to add behavior without rewriting the core.
Got it, Elling.
Liskov substitution principle. This is about inheritance hierarchies. Subtypes must be substitutable for their base types without messing things up.
So if you have a list, an array list should work wherever a list is expected without causing weird errors.
Precisely. It needs to honor the contract of the base type. No unexpected behavior when you substitute.
Okay.
Interface segregation principle. Clients shouldn't be forced to depend on interfaces they don't use. Meaning prefer smaller, more specific interfaces over one big, fat interface. If a class only needs methods A and B, don't make it implement an interface that also has unrelated methods C, D, and E. Keep interfaces focused.
Avoid unnecessary baggage.
You're right.
And finally, D.
Dependency inversion principle. 2 parts here. High-level modules shouldn't depend on low-level modules. Both should depend on abstractions. And abstractions shouldn't depend on details. Details should depend on abstractions.
Sounds a bit abstract itself.
It does, but think about Spring's dependency injection. That's dependency inversion in action. Your high-level business logic depends on an interface, an abstraction, not directly on the concrete database access class, a detail. Yeah. The Spring container handles wiring up the concrete implementation. It promotes loose coupling, makes things way more flexible and testable.
Ah, okay. So Spring DI is a practical example. That's a great overview of solid, really foundational stuff for good design.
Definitely.
Now, let's switch gears slightly. Immutability. An interviewer might ask, what is immutability in Java? And how do you actually create an immutable class?
Right. Immutability means an object's state cannot be changed after it's created. Super useful for thread safety, predictability. You don't worry about concurrent modifications.
How do you make one?
Okay, several steps usually. First, declare the class final. Prevents subclassing, which could introduce mutability.
Okay, final class.
Second, make all instance fields final. They can only be set once, typically in the constructor.
Final fields. Makes sense.
Third, and this is the tricky one, if you have fields that are mutable objects themselves, like a list or a date, you must be careful.
How so?
You can't just assign the reference. In the constructor, you need to make defensive copies or deep clones of those mutable objects. So if someone passes in a list, you create a new list with the same elements. This prevents external code from changing your object's internal state through a shared reference.
Defensive copies. Crucial.
Very. Using a builder pattern can also help manage this construction process cleanly. And finally, obviously, no setter methods, only getters.
Right. No way to change things after it's built. Okay, so that's creating a truly immutable class. What if you have, say, a regular mutable list of employees, and the interviewer asks, how can you make this list immutable so that attempts to add or remove entries throw an exception?
Ah, right. So you have an existing mutable list. In that case, Java's collections utility class is your friend. You use collections.unmodifiable list.
Unmodifiable list.
Yeah. You pass your mutable list to this method, and it returns basically a wrapper view of that list.
A wrapper view.
Yeah, it looks and feels like a list, but if you try to call modifying methods on it, like add, remove, clear, it throws an unsupported operation exception.
Okay. So it stops you from changing it through that view.
Exactly. And this is important, it doesn't change the original list. The original list is still mutable. If something else modifies the original list, those changes will be visible through the unmodifiable view.
Right, it's not true immutability, it's an unmodifiable view.
Precisely. And the exception you get is unsupported operation exception, not, say, concurrent modification exception, which is different. That usually happens when you modify a collection while iterating over it improperly.
That distinction is important. So unmodifiable list is a useful safeguard, but you need to understand its limitations.
Yeah, knowing the difference between true immutability and an unmodifiable view shows a deeper understanding.
All right, great. Let's switch focus again. Spring Boot and application architecture. Super common in Java interviews these days.
Oh, yeah, absolutely. Dependency injection, beans.
Exactly. So a common question. What is a circular dependency in Spring Boot? How can it typically be resolved?
Right. Circular dependencies. They're kind of a classic Spring issue or potential issue. It happens when bean A depends on bean B and bean B depends back on bean A. Or maybe through a longer chain, A depends on B, B on C, and C back on A.
Creates a cycle.
Exactly. Spring usually detects this when it's trying to create the beans using constructor injection. Because it gets stuck to create A, it needs B, but to create B, it needs A.
So how do you fix it?
The most common workaround is to use setter injection for one of the dependencies in the cycle.
Setter injection instead of constructor.
Yeah. Because with setter injection, Spring can create the bean instance first, sort of partially, and then inject the dependency later via the setter method. This breaks the I need you before you created deadlock.
Okay, so delaying one injection breaks the cycle. That leads nicely to the next question. In general, when should you choose constructor injection versus setter injection?
Good question. Generally speaking, constructor injection is preferred for mandatory dependencies.
Mandatory. Okay, why?
Because it guarantees that the object is fully initialized with everything it needs to function as soon as it's created. The dependencies are passed in the constructor, so the object can't exist in an incomplete state. It's also generally better for immutability and testability.
Right, ensures a valid state.
Exactly. Setter injection, on the other hand, is better suited for optional dependencies, things the bean can use but doesn't absolutely require. And as we just said, it's often used to resolve those circular dependencies.
But maybe relying too much on setter injection could hide a design spell.
It could, yeah. If you find yourself needing it everywhere, it might be worth revisiting your component dependencies.
Right.
But it's a valid tool, especially for optional things or breaking cycles.
Okay, that's a helpful distinction. Now, thinking about requests coming into a Spring Boot app, how would you answer this? In a Spring Boot application, how can you intercept incoming requests and add custom logic, like, say, header validation, before the request even hits your controller?
Right, intercepting requests. There are actually a few places you could do this, depending on what exactly you need.
Options are good.
Yeah. So in a microservices world, often an API gateway handles this stuff first. Authentication, rate limiting, maybe some header checks before the request even gets to your specific service.
Okay, the gateway layer, but within the Spring Boot app itself.
Within the app, probably the most common Spring-specific way is using handler interceptor. You implement the handler interceptor interface.
Handler interceptor.
Yeah. It has methods like pre-handle, which runs before the controller method is invoked. Perfect for validation, logging, setting up request context, that kind of thing. It also has post-handle and after completion for logic afterwards.
So pre-handle is the key for before the controller.
Exactly. You could also use Spring AOP, aspect-oriented programming, to define advice that runs before controller methods, but interceptors are often more directly tied to the web request lifecycle.
Any other options?
Well, you could go lower level and implement a standard servlet filter. Filters run even earlier in the chain before Spring's dispatcher servlet even gets involved usually. So that's an option for really fundamental cross-cutting concerns.
So gateway, interceptor, AOP, filter, different layers for different needs.
Pretty much. Interceptors are probably the sweet spot for most typical pre-controller logic within Spring MVC.
Gotcha. Now let's touch on bean lifecycle. Simple question maybe. What are some common bean scopes in Spring Boot?
Okay, scopes define how many instances of a bean are created and how long they live. The default, and by far the most common, is singleton.
One instance for the whole application.
Right, one instance per Spring container. Then for web applications, you have request scope. A new bean instance is created for each incoming HTTP request.
Okay, useful for request-specific state.
Yeah, and session scope, one bean instance per user HTTP session. Useful for things like shopping carts or user preferences.
Yeah.
There's also application scope, similar to singleton but for the servlet context, and WebSocket scope for WebSocket interactions. And technically prototype, where a new instance is created every time it's requested, but you have to manage its lifecycle yourself then.
So singleton, request, session. are the main web ones to know.
Yeah, those are the most frequently used and discussed in web contexts. It's fine to say if you haven't, say, used global session scope much, which is more for portlets. Honesty is good.
Definitely. Honesty about experience is key.
Okay,
Let's shift to the final areas. Data persistence, JPA Hibernate, and microservices architecture.
right. Persistence and distributed systems.
So a really basic one first. What is the core difference between Hibernate and JPA?
Yeah, that's fundamental. The main thing is JPA, Java Persistence API, is a specification. It's an official Java standard, a set of interfaces and annotations defining how object relational mapping should work.
The blueprint.
Exactly, the blueprint or the contract. Hibernate, on the other hand, is an implementation of that JPA specification. It's probably the most popular one, but there are others like Eclipse Link or OpenJPA.
So JPA defines what to do. Hibernate is how it gets done.
That's a great way to put it.
Okay. Now, thinking about dependency injection again. When you have multiple beans of the same type, when is the @qualifier annotation useful?
@qualifier is essential when Spring gets confused. If you have, say, two different implementations of a notification service interface, like email notification service and SMS notification service, both registered as beans, and you try to @autowired a notification service, Spring doesn't know which one you want. It finds two candidates.
Ambiguity.
Exactly. So you use @qualifier along with @autowired to specify the name of the specific bean you want, like @qualifier email notification service. It resolves the ambiguity.
Got it. Tells Spring exactly which one to inject. Makes sense. Now, can you name some common JPA annotations someone might expect you to know?
Sure. There are quite a few key ones. @entity marks your class as a database entity.
Right.
@table lets you specify the table name if it's different from the class name. @id marks the primary key field.
Okay. Basic mapping.
Yep. Then @column for customizing column mapping name, length, nullable, etc. For relationships, you have things like @manytoon, @onetomany, often with @joinTolem to specify the foreign key column.
Relationships, yeah.
For transactions, @transactional is crucial, usually at the service layer. @persistence context injects the entity manager, which is your main tool for interacting with JPA. And if you write custom queries, you'll use @query and possibly @param for parameters.
That's a good list. Cover the core interactions. Now let's zoom out to microservices architecture, a likely question. What design patterns have you used or are you familiar with in a microservices environment?
Okay, microservice patterns. There are several important ones. We mentioned the API gateway pattern earlier, the single entry point. Then service discovery is vital. How do services find each other dynamically? Tools like Eureka or Console often implement this.
Right. Dynamic lookup.
The circuit breaker pattern is key for resilience. Prevents cascading failures when one service is down or slow. Libraries like Resilience4j help implement this.
Stop the domino effect.
Exactly. For managing transactions that span multiple services, which is tricky, you might hear about the Saga pattern or maybe CQRS, Command Query Responsibility Segregation. These are more complex, though.
Distributing transactions are hard.
Very. Another pattern could be the pipeline pattern, chaining services together for sequential processing. When answering this, it's usually best to talk about the ones you actually understand, even if you haven't implemented them all extensively yourself. Explain the problem they solve.
Good advice. Depth over just listing names. Okay, final question area. Security and microservices. How are configurations and especially secrets like database passwords or API keys typically secured?
Oh, definitely crucial. You absolutely cannot hard code secrets in your code or check them into Git. That's rule number 1.
Please don't do that.
No. So common approaches involve using dedicated secrets management tools. Things like HashiCorp Vault, or maybe AWS Secrets Manager, Azure Key Vault, CyberArk Vault.
Centralized vaults.
Yeah. These systems store secrets securely, provide access control, auditing, often rotation. Your application fetches the secrets at runtime when it needs them.
Okay. What if you're using something like Kubernetes?
Container platforms often have their own mechanisms. Kubernetes has secrets. OpenShift has secrets as well. They allow you to inject secrets into your application pods as environment variables or files without storing them in your container image or code repository.
So externalize and secure them using platform features or dedicated tools.
Exactly. The key principle is externalized, secure storage, and controlled access at runtime. Never embed them directly.
That's a vital takeaway for anyone building or deploying services. Secure by design.
Absolutely. And you can see how these questions probe not just coding, but architecture, design principles, security, the whole picture.
Yeah, it really paints a broader picture. So as we wrap up this deep dive into technical interview questions, it's clear, isn't it? Preparation is way more than just, memorizing syntax or specific API calls.
It really is. It's about truly grasping the core concepts, keeping an eye on where the technology is going.
And being able to actually explain your thought process, why you chose a certain approach.
Right. And don't be afraid to be honest about what you don't know or areas where you have less experience. Interviewers usually appreciate that more than bluffing. Listen carefully to those follow-ups too. They often reveal what the interviewer is really trying to understand.
Good point. And always be ready to justify your technical choices. Why this pattern? Why this scope?
And remember, it's also your chance to evaluate them. Is this the kind of technical environment you want to be in? It's a two-way street.
Absolutely. So let's leave our listeners with something to think about, thinking about your own experiences. What's the absolute toughest, maybe weirdest, technical interview question you've ever faced? What made it so challenging? Your stories, your insights. They could easily spark our next deep dive.